Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video series, I am trying to give some supplemental material and explanations of things that are not necessarily covered in our book. In this video, we'll start with chapter 1 and discuss generating functions. In the very first section of the book, we discuss, as an example, the generating function of the Fibonacci sequence. And we explain how when this sequence is put in as coefficient of a formal power series, one can compute, so here are the coefficients, a nice and compact form for this power series, namely this rational function over here. I encourage you to look back at this example and this computation, and I want to discuss now a different computation where we similarly play with the generating function the way we're doing in this section 1.1. I would first like to discuss geometric series. They show up in this introductory chapter already. In particular, we give you a homework exercise that is here and that I encourage you to think about. This is essentially a calculus exercise. But I would like to give sort of a completely alternative approach to a geometric series that comes from long division that you might be used to from polynomials. But I claim we can use long division just as well for formal power series, given some mild conditions. So in this case, I think of the rational function description of the geometric series, namely this rational function 1 over 1 minus z, as the quotient of two polynomials, 1 and 1 minus z. And I will now just do long division with these two polynomials. So just the way you're used to this from high school, I take 1 minus z and we'll divide this into the polynomial 1. So, okay, I think that starts with a 1, and so if I multiply this 1 by 1 minus z, long division says I need to subtract this from the 1 that I'm dividing into. So this here, I believe, gives me the polynomial z. And so now if I divide 1 minus z into c, I get z. Z times 1 minus z, well, that's z minus z squared. I subtract, I get a z squared. And 1 minus z into z squared is a z squared. And I think you can see where I'm going here. So this will continue indefinitely, and this will get you exactly the geometric series. So what you see over here appearing is precisely the infinite series where z to the k. And so by long division we showed that this is the quotient 1 over 1 minus z, and I'm computing this quotient in a formal way as the quotient of two generating functions that happen to be finite. I can think of a polynomial as a finite generating function. Okay, so let's get now to the interesting stuff, actually. So I would like to give you an example of a generating function computation that's actually not in the book. So I'd like to discuss a composition of an integer. So a composition of an integer is just a tuple of some length, of positive integers, and these entries of this tuple, I call this m1 through mn, they sum to my given integer k. So some of you know what a partition of an integer is. This is something similar over here, except that I do care about order. So for example, I might have, the composition 2, 3 for the number 5. That is certainly a fine way to do that. Or I might have the composition 1 plus 2 plus 2. But this is a different composition from the one that's, let's say, 2 plus 1 plus 2. So I think of these as, all three of these are different compositions, and you can see my n changes here. So n is a priori sort of another variable here. Okay, so I'd like to count these compositions. So let's do maybe a warm-up example. So let me do a counting function that maybe I'll call C3 of k. So I'd like this to be the number of compositions of k into 3 parts. I should tell you what a part is. You might realize this already. So these entries in this tuple are called the parts of the composition. Okay, so now to compute the generating function for this counting function, I will do a little bit of sort of generating function setup. So just bear with me for a moment. So let's consider the following product. So I'm going to take sort of a slightly modified geometric series for the variable m1, one for the variable m2, and one for the variable m3. If I multiply this out, a typical coefficient over here will look like, well, a z to the m1 plus m2 plus m3. So what you see up on top is precisely one possible composition of k. And if I multiply these 3 infinite series out, I will end up with all compositions of k into 3 parts. This is, by construction, the generating function that we're looking at. So again, what I will do is I will collect all terms of the form z to the m1 plus m2 plus m3. And what will pop out there is a formal power series whose coefficients count the number of ways to do that for any given k. Now, what you see on the right-hand side over here are the product of 3 geometric series, and in fact, they all look the same, right? So this is a geometric series that starts with the power z to the 1, and so that's a z over 1 minus z. And what I have here, I have this geometric series 3 times. So this is the generating function that we're looking for. Okay, let's modify this. Let's modify this just slightly. So let me do another example. So let's say, let me use O for odd. Okay, so this is another counting function. So let me compute the number of compositions. Of k, again into 3 parts, but I want to demand that each part is odd, is an odd number. I only want to allow that. So, well, what do I have to change? So if I want to compute this generating function, Well, let's do the same thing as we did before. So we have a z to, maybe I'm not writing m anymore, but I need an odd part. So let me write this as 2m plus 1. M starts now, I guess, at 0. And, well, that's just one part. I need 3 parts. So just like before, I'm going to take this to the third power. Yeah, and what you can see is exactly what I did on the previous slide will work here with a slight modification. So my geometric series that appears here is, I guess I have an extra z, and then I divide by 1 minus z squared. Let's get back to the example of the Fibonacci series, because I claim there's a connection over here. Let me define O of k to be the number of compositions of k into any number of odd parts. How should we modify that? If we look at the generating function, well, what I'll do is I'll first introduce a parameter j, and I think of this j as the number of parts. And then for each j, I will have the generating function for the number of compositions into j odd parts, and we basically computed this, right? So this was z over 1 minus z squared, and previously we had 3 parts, so if we have j parts, this generating function will have a power j over here. And now something fun happens. So here the geometric series comes into place again, right? So the sum over j is again a geometric series, but now in the variable z over 1 minus z squared. So we can compute this. And maybe we should clear denominators over here. So if I multiply everything by 1 minus z squared, I will get a z on top and a 1 minus z squared minus z. And I should say, whoa, I've seen this rational function before. It's right up here. So what we've proved is that the generating functions of the Fibonacci sequence and that of the number of compositions into odd parts is the same. And, well, that means that the coefficients in the generating functions have to be the same. And this proves the following theorem, namely that this number of compositions of k into odd parts equals the kth Fibonacci number. So what you've seen here are 2 different ways of computing the same generating function, the same rational generating functions, we call this right-hand side. And there's different uses for that. One use is to have a compact representation of the generating function, and the other one is to prove identities like this, that 2 counting functions or 2 sequences that a priori have nothing to do with each other are the same. I give you a little challenge to prove this theorem on the bottom of this page directly. There's other ways of proving this theorem, but one elegant way is by the use of generating functions. We don't know how old this theorem is. We suspect that Cayley knew this theorem because he talked about very, very similar things, but it's not clear who first proved this theorem. Let me insert one slide and encourage you to look at another book. And this is a famous book, Generating Functionality by Herb Wilf. It's a beautiful book where lots of methods and lots of tips and tricks for generating functions are described in a masterful way. Herb Wilf was not just a master mathematician, but also a master expositor and teacher. And if you want to hear a fun story about Herb, you should ask me sometimes.